Hello everyone. So I just wait a minute or so to make sure I have sound okay. Apparently it's okay, so I'll just start. So just a second. Okay. So hello everybody. Thanks for attending this talk where I'll be talking about flash memory reliability, and especially in the case of real-time systems, which have real-time constraints, but also reliability constraints. So these are lessons learned from a study we did internally in Faire Linux. So just to give a few words about myself. So my name is Gleonec. I work at Faire Linux in the Connected Devices and Product Engineering division. And I have some experience in firmware and hardware design in the years before working with the Linux kernel. So I work in doing BSP and Linux system optimization and development, especially when there is some interaction with the hardware. So this is typically the case here because we have some interaction between the software stack for storage and the hardware, which is the flash memory system, and especially the SATA SSD system. So just before delving deep into the subject, I'd like to take a few minutes to give some reminders about how writing data works in Linux. So this is a full diagram of what happens when you try to write some data in a file in Linux, taken from the Linux programming interface book. And the main point I want to make with this graph is this point here, that there is a kernel buffer cache, which means that when I do a write call to write my data on my disk, I'm not actually writing directly on the disk, but in a kernel buffer cache, which is still in a random access memory, so volatile memory. This means that if my system loses power at this time, I lose my data. So this data can be written to the disk using some functions such as fsync, fdatasync, and sync. I'll give the difference just after. Or by opening my, my file descriptor with the osync option. I'll also give some pointers after that. However, here, this is written on the disk from the kernel point of view, which is not really written on the flash memory, because from the hardware point of view, when you receive some data on the SATA interface here, you do not write the data directly on the non-flash array. You first store them in a RAM cache because you may still need to write on it. So this means that even if you have written on disk from the kernel point of view, from the hardware point of view, your data is still in volatile memory. You can still lose it if you lose the power. There are some instructions in the SATA specifications to synchronize the cache to the non-flash array to ensure that your data is on the non-volatile memory. The NAND is kind of a tricky beast to write to because you don't just write bits and bytes on it. You write and read pages, which are blocks of typically in this example 4 kilobytes. And when you need to write over a page you have already written to, you need to erase a whole block of data which contains multiple pages. This means that small writes on locations that you have already written to are costly because you need to erase a whole block, write your data, write the data that was already written on the rest of blocks to not lose them, and then you have done your modifications. This has an impact because a NAND cell can support about 100,000 erase-write cycles before dropping in quality and not storing data. So because of this, the firmware of the SSD must implement some functions. Typically, a flash translation layer is used to convert the logical block address to physical cell address, which means that even if I write multiple data to the same logical address, it won't be returned on the same location on the non-flash array. And there are also some word leveling algorithms to ensure that the write operations are not just writing to one cell and killing it very fast, and some bad block detection management to detect the cells that are already dead and cannot be written to in order to not lose data. Of course, the file system choice on the software level also has an impact, typically over the resiliency. How does my file system can get over a crash, and how much data do I lose when my system crashes? There is also another impact, which is the write amplification factor. The write amplification factor, to just give a few pointers, is the ratio between the data that is written by the kernel on the memory and the data that is effectively written on the memory. Typically, what the difference is the metadata. For when you write 1 byte of data to your memory, the file system adds some metadata around it, so you don't write just 1 byte, but multiple bytes on the disk. There are some different impacts on the write amplification factors. Typically, the firmware wear leveling and garbage collection increase the write amplification factor because it writes to multiple locations on the drive. File metadata obviously increase the write amplification factor. This is dependent of the file system on how much metadata the file system adds. Journaling, which stores the transactions for reliability, increases the write amplification factor, and obviously compression reduces it. So if you want to write data on the drive, there are basically two methods. Either we open the file descriptor with the OSync or ODirect options. This is typically what you will find when you search on the internet. There is actually a huge difference between both. Even if you, besides the remarks by Mr. Torvalds, the main difference is that ODirect promises that the data will be written directly to the drive via a DMA. OSync guarantees that the write call, when you write data, will not return before data has been transferred on the drive. This is what you want to use because this is what ensures that your data is on the drive. However, it can still be on the RAM cache in the drive and not in the flash memory. So this is still to keep in mind. Another way is to write data normally and then flush at periodic points all the data in the buffer to the drive. Typically, you can use fsync or fdatasync. The difference is that fsync will flush all data and metadata associated with the file descriptor. Fdatasync will only flush the strictly required metadata associated with the flash descriptor to guarantee file integrity. Typically, if you want to minimize the number of write operations, fdatasync is your friend in this situation. So to give a bit of context to the study, we took the case of an industrial data logger. So we want to log data, measurements, logs about how the system is running into a SATA SSD disk. We want to maximize its lifetime because this is the lifetime of the product. If we have to put the product out, change the SSD, this is a costly operation which requires manipulation, and this is not efficient in terms of cost. In terms of reliability, because we are storing logs and measurements, we don't want to lose more than 1 second of data. Again, this is an arbitrary number, and you can make the requirement harder to meet or easier to meet. We're taking the case of an industrial SATA SSD, which has a backup battery. This is important to take into account because this means that the firmware has the logic to save the RAM cache in flash in case of power losses. This means that we don't have to manually flush the RAM cache into the flash memory to ensure the data integrity. Here, the main power losses are the main expected failure mode. Because we are talking about a log type operations, we are expecting multiple small writes per second, typically a few measurements, a few lines of logs, and also some log rotation, so compression plus archival of the logs. Maybe we can add later some higher data rate services, but for now, it's ignored in the study. So the first thing is, how do we actually measure what we are trying to improve? We can't improve something if we can't measure it because we just don't know if it's efficient or not. So typically, to estimate the SSD lifetime, the main thing is to measure the write amplification factor, so the ratio between the data written by the kernel and the data written by the firmware, and measure the quantity of data written over a period of time. Then you can estimate how long your SSD will hold the data you are writing to. To measure the data written by the kernel, you can read proc disk stats, either directly and with your custom tools, or with tools such as IOStat or SRR, which interprets it for you. The smart data can be read also from the kernel. This is some data monitored by the firmware of the SSD drive, which is implemented in the disk firmware, and which measures the number of operations from the firmware point of view. So what's interesting is that proc disk stats is the kernel point of view, and smart is the SSD point of view. So you do a ratio of both, and you have the effective write amplification factor for your application. Other things to take into account is the SSD resiliency. So the best way to do it is simply to simulate your workload, typically using FIO, and then you simulate the failure mode. So typically, in this case, you randomly cut the power. You verify the file system integrity at the next boot. You verify the last modified time before cutting the power, and you can measure how much data you actually lost or not. Because we are talking about a real-time system to ensure that data is returned in a certain time, we need also to measure how much time does a file write take. Typically here, we do a test program where we write some data and we periodically do a fsync or fdatasync call to write the data to the drive. It must be run on the target platform because the result will be dependent on the platform you are using in terms of CPU, in terms of storage, in terms of interface between both, and maybe even in terms of concurrent programs which are trying to access the storage. Typically here, you do not want to write data with the osync flag, simply because the osync flag will make it synchronize the data on the disk at every write operations, which will be much longer instead of just flushing once the kernel buffer cache to the drive. Before delving deep into the choice of file systems, there are some mount options, general mount options, which help every file system. Typically, avoiding writing the access time for files and directories reduce the amount of return metadata. You can do it by simply specifying no at time and no dir time options when mounting your file system, and this makes it prevent writing access time. You can also use the Linux cache to deduplicate metadata write. Typically, in the case of a log, you first write one line, so your modify time is the time you write in the first line. You write a second line, you have to either write a second time the last modify time, or the cache can just deduplicate it, so it writes the first line, the second line, and the last modify time. This reduces the amount of return metadata and is also good for the SSD lifetime because you reduce the write operations. A more tricky one is the partition alignment. Simply to explain simply with a schematic besides, we want the logical blocks Linux sees to be aligned with the pages on the SSD drive. The risk here is having a logical block which is actually on the frontier between two hardware blocks on the SSD, which means that if you want to rewrite that logical block, we have to actually erase both blocks, then write the data on the first one that we want to keep, write the data on the second one we want to keep, then finally write our data. This makes a lot of unnecessary read, erase, and write operations that we want to avoid for both real-time reasons, because it increases the delay, but also for the resiliency, for reliability reasons, because it increases the number of write operations. So now we decided we wanted to have a file system which was efficient for our case, so which was both reliable and which had the lowest write amplification factor possible. We started thinking of XFS, which is old, which is stable, and supported by many companies. So we have a lot of experiences. It's still in the active development, so there are still some new features. And it has one advantage. It has a very low write amplification factor, around 2. So this increases the SSD lifetime and makes it a good candidate. The main problems with that file system is that it does not journalize data, but only metadata by default, which makes it less resilient, which means we can have keep the metadata, but not the actual data. Also, it has a history of being sensitive to power losses, which is bad in our use case because this is typically the failure mode of our application. A second interesting one is nilfs2. It's interesting because it's a log structure file system, which means it maximizes the sequential write. Basically, the disk is seen, the data on the disk is seen as a log, and every data is appended to. It also has some good features such as checkpoints. These are basically snapshots that you can make, and then you can either recover from them, or you can even mount them as another file system to access your file system as it was at the time of the checkpoint. By default, it does not write the access time, and it has been shown to have good performances when you do a lot of small write operations. This is interesting because this is actually pretty much tailor-made for our application, which is storing a log. There are, however, some disadvantages to this file system. First, it has been kind of obsoleted by F2FS, which has a similar structure, but it's more recent and more performant. Also, the main two bad points would be the garbage collection that is done in user space. And in some cases, there has been some cases where the user space garbage collector just crashes, which means that the garbage data that you have to erase just keeps filling your disk until it cannot work anymore because it's full. The checkpoint creation is also very good, but it writes a lot of metadata. So here you have typically a case of either I want my system to be very reliable and I write a lot of checkpoints, but I write a lot of metadata, or I want my system to be more performant and write less metadata, but then I'm also less reliable. It's also a file system that does not support some advanced features such as file system check. So its main concurrent being F2FS, we looked at that just after. So F2FS is a pretty recent system which uses a structure kind of common with inodes. So an inode is typically you have some metadata. Then you can either point directly to data block, or you can have some indirect data block where you point to a block which contain other addresses. These addresses point to data blocks or indirect data nodes with double layers and so on. So you can store some pretty big files. This is interesting in our case because we can expect to have a large log file at the end of the application. But the most interesting thing with F2FS is its structure. Typically, we find, again, the checkpoints. But here we also find that you can have some hot, warm, or cold data segments. This is interesting because this means that some data that we read and write often, typically the log file, can be stored in some hot segments, while some data that we read and write much less often, typically the compressed archives, will be in the cold segments. Now, to give a bit of context about this system, it's very good, kind of like NILFS2. It has a lower write amplification factor, around 2.6. It can create checkpoints in the same way. And also there is some transparent file compression since version 5.6, which is very good in our case because it limits the number of data we actually write. The main problem is that it's not considered stable as of today because it's still pretty recent. It has been developed typically for flash memories, which is good. This is our case. But it has been developed with performance in mind more than reliability. The typical use case it was developed for is simply a smartphone, which means that even if we have little power, we still have a battery, we still have enough power to shut down properly. So it's not made to handle some sudden power losses. And this shows in some studies which have reported that many write errors in corruption scenarios, notably in case of power losses, were not detected. And because they were not detected, they were not corrected. So data was lost. So this is typically the case where you have a file system which is coherent with your application, but because it's developed more for performance and reliability, it does not really correspond to your use case here. So there are some features for reliability, but not enough practically to use it. So its main concurrent here is ext4. So ext4 uses the same inode structure, a similar inode structure with data blocks and then indirect data block pointer. The main difference here is that instead of checkpoints, ext4 uses a journal. So all transactions, write operations are written in it, and we can recover from it. ext4 is stable since 2008, which makes it very stable and even considered a standard. It's used in servers, it's used in desktops. It's the default file system for pretty much all popular Linux distributions now. It's used also in embedded. And because it uses a data journal, it makes its recovery very easy. You just have to read the journal. ext4 is very stable. It's been shown by the same study as F2FS to recover from a majority of write errors, and especially in the case of power losses. So it's very reliable. Basically, it has been developed more with reliability in mind, and it has actually improved reliability over its predecessor, ext3 and ext2. Its main disadvantage is that it writes a lot of metadata, which means it has a higher write amplification factor, and the journal takes space on the drive. In an industrial case, you want to limit the cost of your product as much as possible, so you want to use a small SSD drive, and then you have even less space because there is a journal. Little quirk of that system is also that when you fsync a file, you don't just write the metadata for these files, but for all files in the kernel buffer cache. So if you write to multiple files at the same time and then just want to synchronize one file to the disk, it actually writes the metadata for all the other files too. This could change in the future with the integration of fast commits, which may have been integrated since I've looked at it. So this may change for that particular point. Note that here, if we have a single log file, this is not a problem because when we commit this file with fsync, it will only commit the metadata for this file. There is no other file in the buffer. Because it's an interesting file system in terms of reliability, we try to see how we could increase its performance for our use case. So a first thing to see is the write barriers. So write barriers are basically a system that ensures that the metadata changes are returned to the flash and not to the RAM cache. This is done to prevent, typically in the case of a power loss, if the metadata changes are written in the RAM cache, you lose them and you cannot restore your file system properly. If they are written in flash, you can restore them properly. Except that here, as we have a backup battery, we don't need that feature because anyway, the metadata changes will be written to flash even in case of a power loss. So we can disable it and decrease the write latency, which is good in case of a real-time system. Another option which can be confusing is a DAX option, which is called that way for direct access option. So this may seem very interesting in our use case to decrease the latency of write and operations and to be better at writing fast, to better meet the real-time constraints. But actually, it's not usable here because this is an option made for memory map storage, and SSD blocks devices. So this is not applicable in our use case. But I think it was important to talk about it because it has been confusing for some people. Of course, you can also set the block size according to the SSD in order to better align the partitions with the hardware. But one of the most interesting things is the use of fallocate before writing to the file to reduce the metadata you have to write. Simply because instead of just increasing the size of the log file and thus having to always rewrite the metadata around that, you just create a huge file which has all its metadata already written. The data is not initialized to 0, so you don't have much more write operations. And then you just write to this file, which means the only metadata that will be written again will be the modified time if you disable the access time. So you reduce a lot the quantity of metadata you write and thus increase the SSD life. And one last possibility is to simply not use any file system. So this means you open your dev SD block device directly as a file and you write in it. This is good for some application because you can completely control how you write the data and how much metadata, which metadata you actually use. You can even, if you want, not use any metadata. So you reduce the write amplification factor as much as possible. Except that you have no file system, so you don't have any of the facility provided by the file system. Typically, no permissions, no directory structures, and multiple files. You have to manage them yourself. Also, the resiliency to data loss has to be evaluated and validated in-house. You cannot just rely on a large open source community. So, in conclusion, for this problem, as usual in engineering, there's no one-size-fits-all solution. It's always a compromise. Here, you have to do a compromise between your real-time performances, the reliability you want for your data, and the lifetime of your SSD. Here, if you want to maximize for log type operation of this kind, the SSD lifetime, our proposal is to use two partitions. The first one will be without any file system. You just write in a single log file all your data as needed and with nearly no metadata. So you minimize the write amplification factor as much as possible. And then on the second partition, typically an ext4 file system for reliability, you write the compressed archives to minimize the writes. Here, you have a lot more metadata, but it's a bit less of a problem because you write much less often on this partition. So this concludes this presentation. Thank you for your attention, and I now will be looking at your questions and answering them. So again, thank you for your attention.